I want to look at the cross product geometrically here, and it comes out of one of the algebraic properties of relating the cross product and the dot product. Um, in particular, this theorem right here, that the length of the cross product squared is the length of one vector squared times the length of the other vector squared minus the square of the dot product of those two vectors. Now, the proof of this is rather unenlightening. The way you do it is you say, well, you know, if the vector u is u1, u2, u3, and the vector v is v1, v2, v3, then by the definition, we know what the three components of the cross product are. And to find the length squared, we just square each of those components and add them up. And, you know, this is a binomial. You have to square, you know, FOIL it out. And this is a binomial, FOIL it out. So you get, you know, big long expression in terms of u1, u2, u3, v1, v2, v3. And then I come over here and I look at this right-hand side and I say, well, I can figure out the length of u squared. That's just this. I can figure out the length of v squared. That's just this. And of course, the dot product is this stuff here. And I want to square it, so I better do that. And then you can just multiply these together and you can square that out and collect like terms. And you'll find that you get the same thing here as there. So they're equal to each other. Now, I use that. I mean, it's a purely algebraic proof, just a relationship. You can see that when you do this calculation, you get the same as you do that calculation. But I can use that now so that I can get a geometric interpretation of what the cross product is doing. So this is just the restatement of the theorem up above. But now I know another way of thinking of the dot product is the length of one vector times the length of the other times the cosine of the angle in between them. Squaring this, I've got that squared, that squared, that squared. And then I notice that I've got a length of u squared and a length of v squared in both terms here. So I factor it out, leaving me a 1 from the first term and a cosine squared theta from the second term. I smell a trig identity. 1 minus cosine squared theta is sine squared theta. And so this thing is now equal to this. Taking the square root of both sides, I've got that the length of the cross product is the length of u times the length of v times the sine of theta. Now, technically, I mean, lengths are positive, so square rooting a square gives me back to the positive. Sine theta might be positive or negative. So square rooting the sine squared, I really should put absolute values around it. But then when I'm thinking about what I'm doing, u and v are two vectors. And when I measure the angle between two vectors, I measure the smallest angle. That's going to be somewhere between 0 and pi. And the sine, if you think about the sine curve, right, from 0 to pi, it's always positive. So I don't need to worry about the absolute value there. I've seen some textbooks define the cross product this way. They say, given vectors u and v, the cross product is a vector of length this long, length of u times length of v times the sine of the angle in between them, and its direction is perpendicular to both u and v as determined by the right-hand rule. So for instance, if this is u and this is, so if this is u and this is v, then the right-hand rule says, take your right hand. Now I gotta be careful. I always used to be backwards because I'm holding my pencil in my right hand. So I put that down and I say, okay, I'm going to take my fingers and point them in the direction of u and curl them towards the direction of v through the smaller angle. My thumb, which is pointing right up at the camera here, is pointing in the direction of the cross product. Right? If I did it the other way around, v crossed with u, I'd be starting and I got to be able to turn my fingers this way to be able to curl it like that, and then my thumb is pointing down into the screen there, into the page. So the direction matters, and we determine that by the right-hand rule. So anyway, I've seen this given as a definition, and then you prove it's equal to the algebraic definition that we gave. This is really kind of cool because it looks very similar to the dot product, where the dot product of u and v is the length of one times the length of the other times the cosine of the angle in between them. That's already a real number, right? Dot product gives you a real number. Cross product gives you a vector, but you take the length of the vector, that's a real number, and it's equal to this. Now, we use this to do a little more geometry, and that is calculate the area of the parallelogram. If I've got two vectors, u and v, I think of them as determining a parallelogram. Let's see how well I can draw my parallelogram there. And the way you calculate the area of the parallelogram is essentially base times height. Let me put a height in here. And the reason that works is, this is perpendicular, is if you think about this triangle right here, cut it off, move it over to here, so that it would end up being right there, well then you've just turned your parallelogram into a rectangle with the same area, and the area is the length of the base times the height. So the area here, let's go back to blue, is going to be the length of the base, which is the length of v, times this height here. Well, to calculate the height, I would need to know this angle right here and that hypotenuse. Well, I know the length of the hypotenuse. I know this side. I need to find the opposite side. So I need to find that length, which is the length of the hypotenuse times the sine of the angle in between, the sine of that angle right there, right? Finding the opposite side. So area is the length of v times the length of u times the sine of the angle, which is what we just calculated up here, the length of the cross product. So the length of the cross product is the area of the parallelogram determined by those two vectors. Now, as you work through some of the homework problems, you'll find that sometimes they ask for areas of parallelograms, sometimes they ask for areas of triangles. Well, areas of triangles would just be cut that parallelogram in half, right? So it would be 1/2 of the length of the cross product. Anyway, there's some geometry related to the cross product.